Well, we've been looking at how to differentiate in physics. We've looked at differentiating polynomials and trigonometric functions, and now we're going to have a quick look at differentiating exponential functions. Now, all sorts of physical phenomena are modelled with exponential functions. Often it's exponential decay, but it could be exponential growth as well. And here are 4 examples just from A-level physics. The first example here is the number of nuclei within some radioactive sample, where n0 is the original number of radioactive nuclei and t is the time. Lambda here is called the decay constant. The second example here is the potential difference across a capacitor as it discharges. V0 is the initial potential difference across the capacitor when it was fully charged, and R and C are the resistance through which the capacitor is being discharged, and C is the capacitance of that capacitor. The third example here is the amplitude for a lightly damped harmonic oscillator, where A0 is the initial amplitude and K is some constant that tells us about the decay of that amplitude over time. And the last example here is a bit of an interesting one. That's a modelling of cooling. So T0 is some initial temperature, and T is the temperature at a time, little t. TR here is the room temperature towards which temperature of the body is converging. And again, we've got some constant K. Now, in all these examples and many, many more, where there's some sort of exponential function, often we will just say, it looks exponential, let's model it with an exponential and see whether the results match. If the results match, we can work out what these constants are. You'll also notice all these exponential functions have the same base, e, which is a very special number, 2.72-ish. So let's keep things general and say I've got some function of x, which is in this form here. So a could be the base e, or it could be any other base. It could be base 10, and you'll often find things in base 10 in astronomy. But here, a is just some arbitrary base. The x here is referred to as the logarithm, or the exponent, or the power, or the order. It's got a lot of names. So let's change this. Let's write this as y as a function of x. And if you remember, we were trying to find the gradient. So we're going to differentiate this function with respect to x. Very often, x might be a time if we're talking about rate of change of something. Now, in the first video in this series, I showed you that what you do is add a small amount onto x, and then use that to find what the gradient of the chord is. Then make that extra bit you add smaller and smaller and smaller. Well, before I was using the letter e for this extra bit we add on, but because of that special number e that appears everywhere, that's probably a bad idea. So I had a look, and it looks like people that go through this derivation tend to use an h. Well, who am I to argue? Let's use an h as well. And just a reminder of what we're doing here, we've got a point down here where we want to find the gradient, some arbitrary point x, and the value of y at that point is ax, and some point up here which is separated, so it's h further along than x, and the y value is x plus h. These are the coordinates of those 2 points. The chord that connects those 2 points has a steeper gradient in this picture, but it doesn't matter what the function looks like. Just the idea that as h gets smaller and smaller, the gradient of that chord gets closer and closer to the gradient of the tangent at that point. The gradient is the difference in the y-axis divided by the difference in the x-axis, and the gradient is the derivative. So, a change in the y-axis divided by the change in the x-axis is this. Then divide that by the change in the x-axis, which is x plus h minus x. And you can see the x's cancel out straight away. But then we can use some special rules up here. This term here is equivalent to this term here. That's the laws of logs, and maybe I'll do a video about that later as well. Now, the a to the x can be factored out like this. And now here's a really clever bit. Anything raised to the power of 0 is equivalent to the number 1. So we can write that like this. In fact, h is the same as 0 plus h, so let's just write that. I've done 2 things here. I've done the 0 plus h, which seems like a really odd step to do. And I've also taken the ax down here and said ax is multiplied by all this lot. And the reason why I've done that is because this term here is equivalent to this term here when x has the value of 0. So this term here is delta y by delta x when y, which is a function of x, has x as 0, which is why I've written it like this. Delta y is a function of 0 divided by delta x. Now, at this point here, my simple physicist's brain is looking at this expression, and it's saying, well, h is approaching 0. H is getting smaller and smaller. So if we say, well, let's just set h to 0. Let's see what happens. If h is 0 here, we end up with a to the power of 0, which is 1. And we've got a to the 0 plus 0, so that's still just 1. And those two are subtracted. And that's divided by something that's getting closer and closer to 0. So we end up with 0 divided by 0. And my simple physicist brain is seeing that and getting quite alarmed. And mathematicians will be screaming out, saying, no, you can't do that. What does 0 over 0 equal? Because, of course, 0 divided by anything is 0. But anything divided by 0 is undefined. So this is undefined. But then anything divided by itself is 1. It'd be really nice if this equaled 1. So what's the answer? So the question is there a value a can take that means this term in the square brackets, this term here, is the number 1? Because that's the interesting exponential, is when the base is e. There's a reason for that. So what we're looking at is, let's take that case, a equals e, that special number we mentioned before, and have h approach a 0. And as h approaches 0, does this expression approach 1? Well, an easy way to find out. We'll plot a graph. So I'm using Desmos here as my graphics calculator. It's a free online graphical calculator that you can use. And I've plotted the function a to the power of x minus 1 divided by x, which if you look here is the expression we've got. A to the power of 0 plus anything is just what you're adding. So a to the power of h minus, this is 1, divided by h. So I've just replaced the h's with x's. And this expression here is then what's the same as in the square brackets. We want to look for the special case where this value is equal to 1 when x equals 0. Now, if you plot a graph of a to the x minus 1 divided by x, the curve looks a bit like this. And then you can look at what happens when x equals 0 by looking a teeny bit to the right of when x equals 0 and a teeny bit to the left of when x equals 0. And as you get closer and closer and closer to 0, you converge towards some number. Now when a equals this special number here, which we call e, Euler's number, when a equals that number there, this function approaches 1 as x approaches 0. And look, if the number was a little bit bigger, then we would cross that y-axis at a number greater than 1. And if it were a little bit smaller, less than 1. But when a equals that special number, about 2.7, a little bit more than 2.7, then we cross the y-axis at 1, which is what we needed this function to do. Or in this case, we're not saying h equals 0, we're saying h approaches 0. And as that happens, this function approaches 1. I'll leave it to the mathematicians to make all that make sense to you. As a physicist, I plotted a graph. I was happy with the outcome. I'm going with it. So let's rewrite that expression now. Instead of a, we've got e. That was that special number, which did this special trick on the graph. And instead of a delta, because we're taking the limit that h is approaching 0, we'll use a d. That's our little sign that we use in calculus. And so the derivative here is going to equal e to the x multiplied by 1, which is just e to the x. And there we have it. Well, what if we want to differentiate an exponential function, but the base isn't e? What do we do then? So you can see when the base is e, the exponential function is very easy to differentiate. It just doesn't change. But what about when the base isn't e? A general case where the base is a. What can we do then? Well, then we can use a property of logs, of logarithms. This property here, ln, is shorthand for the log to the base e. We call it the natural log. The log to the base Euler's number. So e raised to the power of the natural log of b is just b. That's because raising a function to the power of e is the inverse of taking a logarithm of a function. So these are inverse functions. So I've just written over here the basic notation for logarithms in case you don't know it or you've forgotten it, and I can do a video later about logarithm. Log to the base 10 of 10 is 1, which means 10 raised to the power of 1 is 10. log to the base 10 of 100 is 2. And that means that when our base is 10 and we raise it to the power of 2, the answer is 100. Log to the base 10 of 1000 is 3. That means when our base is 10 and we raise it to the power of 3, 10 to the power of 3 is 1000, and so on. So in general notation, we could write this. Well, we know how to differentiate e to the power of something. Because logarithms and exponentials are inverse functions, then we can do e to the power of log to the base e of a to the x, and that's just going to be a to the x. These are inverse functions, so they cancel out. But one of the properties of exponentials, when you write them in this form, log to the base e a to the power of x, is that you can take that exponent and bring it down here. And you can see that in this expression here. If we take the x and bring it down here, then log to the base a of a to the power of 1, well, that's just 1 by definition. So you end up with x multiplied by 1. From this figure here, you can see how that works. So what I've now got is e to the power of something. And I know how to differentiate that. But this means we have a function of a function. The first function here is x is multiplied by the natural log of a. And the second function is it's all raised to the power of e. So we use the chain rule. Remember, with the chain rule, we could split a derivative apart. So d a to the x divided by dx is the same as d e to the some other variable, z, divided by dz times by dz by dx, where z is the exponent of this number, and you can see from the expression above, that's x log to the base e of a. And there we have it. That was very straightforward to differentiate. dEz by dz is just e to the z, and dz by dx, or natural log of a, is a constant, because a is a constant, multiplied by x, which is our variable. So when we differentiate this, the constant can come outside the derivative, and dx by dx is just 1. So this just becomes log to the base e, or the natural log of a. And if I write this with the notation ln means the natural log, save me a bit of space there. Natural log of a multiplied by, I'll just swap these two terms around, e, and I've substituted in for the z, natural log of a to the power of x. We've just gone all the way back to here again. Remember, again, that the x can be before the natural log, or it can be up here, because of this identity up here on the top right. But e to the power of natural log of a to the power of x was a to the x. So the first derivative of a to the x is a to the x multiplied by this constant, which is just the natural log of a. So that was differentiating exponential functions. And now we've got an idea for why e is such a special number. But in the next video, we're going to introduce the idea of integration, starting with what the physical significance is of areas.